Okay, I messed up. I accidentally recorded without audio the last video. So to hopefully make up for it a little bit, I'll still upload it. It'll be like, you know, I'll quickly walk through all the problems, um, just like conceptually here, um, just so people still kind of like know what's going on. They don't have to trace through the entire work. Here, this is saying current after a switch is closed immediately. Here, the capacitor, it starts or it reduces the amount of amps that come through it over time, but initially when it's closed, that full thing or like current going through it. So you can effectively just treat it as there's no capacitor there, and it's just this resistor diagram. You solve it, boom. This classic resistor diagram, there's three different like paths, so they're all in parallel. Just solve it, you're done. This is, one of the ones where, you have separate currents, like three separate currents separated by junctions, and then you make rules or the junctions to some different currents up, and then you walk through the loops. I recommended using the loops for which you have a current, like a single current here, because then it's easier to just sub it in these equations, then solve the system of equations and get your currents. Here, this one, a voltmeter is attached to R2. What that effectively means is that you have an extra resistor in parallel with R2. Solve, you can eventually solve for the V on this R2 and the V on this R2 if there's a voltmeter attached to it. Take the percent error, you'll get this answer. Here, like, look at the formula sheet. You'll see that radius, all these factors are held constant, is proportional to velocity. The period here is not proportional to radius at all, so they're the same, whereas here, greater velocity goes to the one. Here, this is just setting electric field and magnetic field equal to each other, solving, use right-hand rule to find the position where it's opposing the direction of the electron in the electric field. Here, sides obviously cancel out, so you just look at the force on a line here for this this top part of this line with the current going to the left here. Solve for that. Here, normal vector, or sorry, the magnetic moment, it's normal to this loop. And I will explain this a little bit more in depth. You curl your fingers around, like in the direction of the current. The normal vector there is where your thumb's sticking out. That's the magnetic moment. Now the magnetic moment, it wants to essentially align itself parallel to this B vector. So now it's facing down. It wants the fastest way to get there is just for it to turn this way counterclockwise. So that's what will occur. Here, what you can just do is solve for the net pull in each direction. I like to say like the net like field directions and the corresponding amps that are corresponding to each direction, and then just use this equation for line forces because these are lines coming out. And all of these are held constant, but you want to make sure you're adding the i's on both the x and the y direction, so you have to use this like Pythagorean formula. Net force on the cancel. You have two sides, right? This closer side, it makes this, again, this is just line formula, but this closer side will have like this 1 over 1 as its distance. The further side will have 1 over 3. And then you use like this formula, and you end up getting this answer. Here it's pretty similar. So these two, one wire line and one circular wire, their fields oppose each other on this center dot here. So you have the, what is this? This is, I think this is the circle, and formula for the wire, and you just subtract them. Here, what you do is, we see that there's 7 going like into the board here and 6 coming out of the board, and you basically align for direction this like loop would generate its current in. So this loop, it's heading in like this direction. So its field would go into the board. So we take that as positive. So 7 minus 6 gives us 1. Here, this is one loop inside of the other with alternating amps inside the outer loop. This is an EMF problem. We basically solve for EMF where the area of the inner loop is held constant, but there's an alternating magnetic field. The magnetic field is defined by that this equation here, where the I is alternating. So it's like sine of omega t. When you differentiate, the omega comes out, and you end up with something like this. This 2 pi over r times I times this omega from the sine term. And the sine term can use it because we're looking for like the max amplitude of the EMF. And so then you just have to multiply the area times that resulting change in the magnetic field, you get your answer. And also, if you're given hertz, you got to make sure that is in rotations a second or like cycles per second. If you want an omega, that has to be a second. So there's 2 pi radians in a full rotation. So you just multiply by 2 pi. Anytime you get hertz, multiply by 2 pi to get the omega. Very important. This is plug and chug in a formula. This is an R. Yeah. This is a another flux problem. The magnetic field is constant, but here the area inside of the field is changing, and the amount it's changing by is proportional to it's actually the length times the rate at which like this piece is changing, which is the velocity, right? You have a velocity amount times the length leaving each second, so you'll end up just getting BHV for your formula, and then you use that to calculate the power. Here you have a solenoid, and you're basically given an EMF, and you're given basically everything you need. The formula for B field in a solenoid is this mu naught IN. So you can like plug that all in, and that will give you the area of the solenoid. And then when you solve for the EMF, right, the area is held constant, so you just like shove it at the end, and then here it asks you the current at the specific 20 amps. So instead of like integrating the derivative here, you just put in the 20 amps. You transform that into the B field by multiplying by the N and the mu naught O, which get canceled by this other term that we found over here, and basically you get your answer. This is just plugging. This is an LC circuit. You can find omega like this because you will need it. This is an RLC circuit. It's plugging. You can find your omega like this. And also cycles, if you want to find the time. Basically, this, where did they give you? Oh, basically, yeah, if you find this, what we found omega was 1,000. So that's in radians a second. If you want back to rotations or cycles, you have to divide by 2 pi. That gives you rotations a second. If you want to find the seconds per rotation, you flip that. So 2 pi over 1,000. If you multiply that by 2, you'll get the amount of time it takes to do 2 full rotations per rotation. You multiply that by 2. That gives you your t here. Phase angle, just use this formula here, and you can cancel the xc because there's no capacity. And this, even though it says EMF source here, this is hertz. So this is actually your rotations a second. So it's just describing the EMF force, but this is not the voltage. This tripped me up as well. But yeah, this is describing the. You can just use this to find the omega. And then finally, here, maximizing the power. Basically, to maximize the power, you just have to maximize the amps. And in order to do that, you want to minimize this denominator, which means you make this equal to 0. XL equals XC. This occurs. You solve it. Again, really sorry. I'm going to record right now spring 2024. which I do think is a little harder. I did say at the start of the video that this was like the easiest one of the three I had looked at. So I don't want to say you're not missing out on much, but if you want, or maybe you can look at the other video I'm posting. I'm posting like the full version with no audio, but sorry about that. Again, I'll get the next one up very soon.